Good morning, friends. So once again we shall continue with the last part of the ionic equilibrium. That is, Ka and Kb values, dissociation constant of weak acid and dissociation constant of weak base. Now pK value and pKb values, these two things we have to discuss. Look here, pKa is defined as, so what you know about Ka value? For example, acetic acid, if you can write H plus H2O, H3O plus. So K value is the dissociation constant, ions in the numerator, correct? Acetate ion concentration, hydronium ion concentration divided by water is a solvent excess, its concentration is unity, acetic acid concentration. So if a high value of Ka means the acid is relatively stronger acid because ions are in the numerator. If Ka value is more, ions are more. Ions are more means ionization is more. Now what happens when you calculate pKa? Look here. pKa is defined as like pH, negative logarithm of K to the base n. K depends on nature of the acid and temperature also. So negative logarithm of Ka. For example, acetic acid at 298 Kelvin, Ka 1.8 into 10 raised to minus 5. So negative logarithm of 1.8 into 10 raised to minus 5 minus log 1.8 to the base 10 plus 5 log 10. You understood? It is not minus or minus. So this becomes minus 0.2553 1.8 value plus 5. This is 4.7747. This is pKa. Suppose if you calculate it for formic acid HCOOH, Ka value 1.7 into 10 raised to minus 4, and if you work out this is almost in the range 3.7 if you calculate similarly. So it means if you look at the Ka value, formic acid is stronger acid, pK value is lesser, say this. Same as pH. pH is a general term to explain acidic or basic nature of fluids. This is Ka value and pK value for expressing the acidic nature of weak acids. So what is the understanding? Lesser the pKa, stronger is the acid among weak acids. A difference of 1 unit of pKa makes strength 10 times. Difference of strength is 10 times. Now I write 4 acids. So it means formic acid is strong. This is strong because this K is strong. So what is this? Lesser the pKa, stronger is the acid. Is it okay? For example, A, B, C, D are 4 acids whose pKa are 9.1, 8.3, 2.1, 4.6 respectively. Which is strongest and which is weakest? 2.1. C strongest because 2.1. 9.1. A weakest. Is it okay? Then similarly pKb values. pKb negative logarithm of Kb. Dissociation constant of base. One more very important thing. For conjugate acid base pair. For conjugate acid base pair. 298 Kelvin. So you already know Ka into Kb is 10 raised to minus 14. I told you. So it only means that pKa plus pKb is 40. Similar. So if you know Ka value, you can find Kb value of the conjugate base. K and Kb, if you know, you can find pKa. For example, Ka 10 raised to minus 5. What about Kb? 10 raised to minus 9. Then what about Kw? Minus 40. What about pKa? When you take negative logarithm 5. What about pKb? 9. What about pKw? Is 46. Hope you are following. K into Kb is 10 raised to minus 40. Conjugate acid base phase. pK plus pKb is 40. So by knowing the pK value, you can find the strength of acids. By knowing the pKb values, you can find the strength of bases. Same note, huh? No. Lesser the pKb, stronger is the base. Similar examples can be asked. Okay. Let's note this. This is one more learn. Next one is dissociation constant of polybasic acids. Dissociation constant of polybasic acid. So far I have discussed only monobasic acid like acetic acid. Now for example, polybasic acid H2A dissociates into H plus Ha minus. Once again, you call this as Ka1. Ha minus further dissociates into once again H plus and A2 minus, and you call it as Ka2. What is the expression here? Tell me. That is H plus concentration into Ha minus concentration by H2A. What is Ka2? It is H plus concentration into A2 minus concentration divided by Ha minus concentration. When you take H2A directly as 2H plus A2 minus, what will happen? What is K? H plus square A2 minus divided by H2A. If you compare this to multiply Ka1 into Ka2, so this is the numerator, this is the denominator. H plus, both are in the numerator, H plus square. You get the same Ka equal to K1 into K2. Normally, K1 is much greater than K2. One example I take H2, SO3 is a weak acid. sulfurous acid. So it ionizes to 2H plus SO3 2 minus, and K will be H plus square divided into SO3 2 minus divided by H2SO3. So then what is K1 value? How do you write K1? H2SO3 gives H plus HSO3 minus. Next HSO3 minus gives H plus SO3 2 minus. So this is K1, this is K2. How the K1 and K2 are related to K? Say K equal to K1 into K2. So here K1 is greater than K2. For example, for H3PO4 tribasic acid, this is a tribasic acid. H3PO4, 3H plus PO4 3 minus. Again, I think you can write one by one. You can ionize the acid. So here, what will happen finally? K equal to K1 into K2 into K3. Is it not? This is what will happen. You can write all those steps and see like this. I have written here. Like this, you can write. So this is. Some of the strength of acids can be predicted. Please remember, strength of acids across a period, for example, across a period, I tell you, you all know second period. For example, H2O is lesser than 1 minute. I'll start from CH4 lesser than NH3, lesser than nitrogen oxygen H2O, lesser than HF4. Please note this. Across the period, if you move, acid strength increases. Methane, weakest acid. Next. Carbon, nitrogen, oxygen, fluorine. But down a group, you can move in any group. I will move in this group. Okay? See, H2O weaker than H2S, weaker than H2SC. Oxygen, sulfur, selenium, tellurium, correct? Polonium, radium, H2T. So H2T, down a group, acidic strength increases. This is also another important thing. So these are all mostly related to entrance examination aspects. So along the period, HF is the strongest acid. They are all weak acids, remember. Water is weakest, but down a group. Okay, we can take another this one. HF less than HCl, less than HBr, less than HI. Same thing, no? Because what is the group? Chlorine, bromine, iodine. So this is how strength of the acids also can be predicted. Please note all these things. So we are almost at the last part of the chemical equilibrium. One more heading is remaining, that I will start. Note this. Solubility and solubility product of a sparingly soluble salt. Sparingly soluble salt. What does it mean? See, part of the chapter, solubility and solubility product of a sparingly soluble salt. Sparingly soluble salt, for example, AgCl. What are sparingly soluble salts? So those salts which can be precipitated from a solution. See, I'll tell you detail little later now. Whenever you mix two clear solutions, you are done practicals, right? Whenever you mix two clear solutions looking like water, immediately you will get a precipitate like milk. Well, because that is not soluble. That is why it is precipitated. Such salts are sparingly soluble salts. Sparingly is not slightly, very less. Sparingly soluble, so less soluble. Otherwise, they would have used the word partially soluble. No, it is sparingly soluble, not partially soluble. Some of the salts are types like AB type, A2B and AB2 type, A2B3 type, like this. For example, AB type, silver chloride, AgCl, barium sulfate, BaSO4, lead chloride, this is A2Br, Ag2, silver chromate, lead chloride, these are all precipitates. Arsenic As2S3, arsenic sulfide, As2S3. So these are all some of the salts which are called sparingly soluble salts. So I have written heading solubility and solubility product. Again, what is solubility product? It is equilibrium constant. Let us start with the AB type. AB type. Consider a sparingly soluble salt. Sparingly soluble salt. AgCl solid gives Ag plus in the solution plus Cl minus in the solution. Okay, plus Aq we can write plus aqua. Okay. So as usual, how do you write? KSP, solubility product, equilibrium constant. Ag plus concentration, Cl minus concentration divided by AgCl solid concentration. Is it okay? So by convention, I already told you, solid concentration is unity. It is undissolved, which establish equilibrium with the ions that are soluble in the saturated solution. Look here, in the saturated solution at constant temperature, a precipitate is observed. Partial ions are observed. There is a dynamic equilibrium once again. Some of the precipitate dissolves into ions. Some of the ions re-precipitated back. So you know all equilibriums are dynamic equilibrium. That is all there. Now, since this is unity, what do you write? KSP is equal to Ag plus concentration into Cl minus concentration. Now, if I call this Ag plus as S, where S stands for solubility. What S stands for? Solubility. Then what will happen? KSP equal to S square or S square, or you can say S is equal to square root of KSP, where you can say where KSP solubility product and S is solubility in the, what is the same unit, mole per liter. Solubility in the mole per liter. Okay, one more I will show you. For example, lead chloride, Ab2 type. Ab2 type I will show you. PbCl2 is a solid which is a precipitate. Pb2 plus 2Cl minus. Here solubility corresponds to lead ion and not chloride. Notice, because chloride ion is double, that is 2S. So this also is one of the important things to understand. Lead ion concentration corresponds to solubility. Now you tell me solubility product. You tell me solubility product. Okay, Ksp equal to lead ion concentration, chloride ion concentration to the power 2. This is not common to you. This is a common to you, is it not? Number of moles are always raised as powers. So lead ion concentration is S. 2S square. It becomes S into 4S square. 4S cube is Ksp. So if solubility product is given, solubility can be calculated and vice versa. Now define solubility product. Definition of solubility product. The product of molar concentrations of the ions raised to the respective stoichiometric constants in the saturated solution of a sparingly soluble salt, right, at constant temperature. This is solubility product. You just see the expression, you will understand. The product of molar concentrations of ions raised to respective stoichiometric constants in the saturated solution of a sparingly soluble salt is called salt at constant temperature is called solubility product. So like all other equilibrium constants, this also depends on temperature and nature of solvent. For AgCl, this is of the order 10 to the power minus 10, 10 to the power minus 12 like this. Solubility product. That means solubility is so less. What is solubility? What is solubility? The molar concentration of ions. The molar concentration of ion in the saturated solution of sparingly soluble salt. What is the unit? Unit of solubility, mole per liter, same as concentration. If you want one simple problem I work out, just see. Simple problem I work out. the solubility product of AgCl at silver chloride 298 Kelvin is 1.8 into 10 to the power, or you can say simply 4 into 10 to the power minus 10 at 298 Kelvin. 4 into 10 to the power minus 10. Find solubility. So it means AgCl, what type it is? KSP equal to S square, AB type. So 4 into 10 to the power minus 10 equal to S square. S equal to root of 4 into 10 to the power minus 10. 2 into 10 to the power minus 10 mole per liter. This is solubility. How to calculate solubility? Or if solubility is given, you can find solubility product. Now, one important thing you try to understand, okay? I think these are the things you have to know. One important thing you have to understand. Suppose, what is solubility product? I will make it very clear. BaSO4, barium sulfate, KSP value is, say, roughly 10 raised to minus 12. In the 10 raised to minus 12 range. Think. Now let me see whether barium chloride will precipitate with mix 2 test tubes you have. One barium chloride 10 to the power minus 6 molar. Another solution is zinc sulfate 10 to the power minus 8 molar. So if you mix barium chloride and zinc sulfate, according to the equation you get barium sulfate and zinc chloride. But will it precipitate? Will it precipitate? Because solubility product of barium sulfate is 10 to the power minus 12. I will take the ionic product. Barium ion concentration. Both are salts, strong electrolytes, 100% ionizes. Barium ion concentration into sulfate ion concentration. And take barium ion concentration, same as barium chloride, 10 raised to minus 6. Sulfate ion also same, 10 raised to minus 8, 10 raised to minus 40. Less than KSP. Physically available ions in the test tubes product is less than solubility product. Solubility product in the saturated solution is more. If some more ions are also there, it will be soluble. This is soluble. No PPT, no precipitation, because ions are less. Then this is what I want to convince you. When KSP greater than ionic product, same ionic product less than KSP, same as KSP more than ionic product, physically available ionic product. KSP is more than ionic product implies unsaturated solution. KSP less than ionic product. Okay, you know how much is the solubility product. This is the solubility product for this salt at this temperature. Have some ions, increase the concentration. Since they won't precipitate because they are completely soluble salts. Now, when you mix the two, if KSP is less than ionic product, ions will not be soluble. Ionic product is more. What will happen? Precipitation. Precipitation. Understand? Then KSP equal to ionic product, neither precipitation nor unsaturated. Saturated solution. So now you have done so many practicals and all. You have seen so many precipitates. Color precipitates also. But have you thought so far why it is precipitated? Its solubility product was lesser. Through strong electrolytes, you have added those ions. The salt realizes its solubility product, which is less. Then immediately, all those ions which are more than the solubility product, they start aggregating and develops a solid. And you can say like this. You can do magical stuff to some unknown people, villagers and all. You can take 2 test tubes or 2 bottles. This is water, you can say. I am mixing water, I am producing milk, you can say. What is those solutions? One is barium chloride, other one is aluminum sulfate. Both looks like water. When you mix the two, you get barium sulfate. Barium sulfate is a precipitate. And it looks like milk. So a magic also can be done. Why it has precipitated? Because ionic product is now more than solubility product. Or solubility product is less than ionic product. So these informations also you have to understand. Now for the third type, one more type also you can write. For example, general equation also you can derive. For example, AS2S3 type, KSP becomes 108 S to the power 5 because this gives 2 AS3 plus concentration, 3 S2 minus concentration, 2S, 3S solubility. So none of the ionic concentration corresponds to solubility, not this. Because this corresponds to 2S, this corresponds to 3S. Suppose if arsenic ion concentration is given, divided by 2 will give you solubility. Okay, the last one is common ion effect. Now you see what will happen. AgCl is a precipitate. Ag plus Cl minus. Suppose if I add NaCl, which is a strong electrolyte, it supplies plenty of chloride. What will happen? Now this corresponds to S, this will not. Because NaCl Cl minus or AgCl Cl minus. Cl minus is 1 and same. Now this is common ion. Right side becomes more. Correct? Not equilibrium. Leach-Atelier principle. If right side becomes more, what should happen? Left side should be favored. That means precipitation takes place. Precipitation takes. So ionization, I use the word ionization of AgCl is suppressed. Suppressed. This word have you understood? Suppressed means decrease. So what is common ion effect? Suppression in degree of dissociation of weak electrolyte. Weak electrolyte due to the addition of strong electrolyte having an ion with weak electrolyte is called, having an ion in common with weak electrolyte is called common ion. So what happens to solubility with common ion? Solubility decreases. Effect. What is the effect? Effect of common ion? Effect of common ion? Solubility decreases. Okay. So this is all about what? Solubility products of sparingly soluble salts. Some simple problem can be worked out based on solubility products also. The last part, that is buffer solutions. Buffer solutions. See, think this is a beaker having HCl. Maybe pH is 4. pH is okay. Sorry. This is the beaker having NaCl. Both two beakers having NaCl. NaCl is a salt of strong acid, strong base. pH is 7. pH is 7. 1 drop HCl you add, 1 drop NaOH you add. Here pH becomes 11. Here pH becomes 4. 4 or 3. 1000 times hydrogen ion concentration decreases. 1000 times hydrogen ion concentration increases. 10. By adding single drop of HCl or Na. That means that much pH is not changing. pH is that much changing. But I have got a buffer solution. What will happen if you add small amount of acid or this? Its pH will not change. Its pH will not change. Such solutions are buffer solutions. Those solutions which are resistant to change their pH values upon adding smaller amount of acid or base are called buffer solutions. And these are ordinary solutions. They are not buffer solutions. And what are buffer solutions? What are buffer solutions? Those solutions which are resistant to change their pH values upon adding smaller amount of acid or base are called buffer solutions. Then give some examples of buffer solution. Give some examples. I will give you some examples. Example. See, it cannot be a single solution. A weak acid plus its salt with strong base. This is one buffer. This is acidic buffer. And pH is less than 7. One example is acetic acid plus its salt with a strong base, NaOH, CH3COON. Acetic acid and sodium acetate is an acidic buffer. And to this, if you add acid and base, see, pH will not change. Details are not there in your syllabus. Only elementary idea has to be discussed. So explanation is there why it is and all. Second one is basic buffer. I will write a weak base plus its salt with a strong acid, and this is called basic buffer. pH more than 7. Weak base, ammonium hydroxide. This is a weak base plus its salt with strong acid, HCl, ammonium chloride. This is a basic buffer because pH is more than 7. Neutral buffer is also possible. Neutral buffer, a salt solution of weak acid with the weak base whose Ka equal to Kb and the pH is 7. So you take two substance, acid and base, whose Ka and Kb are equal. That means then this thing. And for this salt, I will take acetic acid and ammonium acid. Ammonium hydroxide. So ammonium acetate is one such solution. This is formed by acetic acid and ammonium hydroxide. The pH is 7 because Ka and Kb are same, or pK equal to pK. So details are there, equations are there, Anderson's equation to calculate the pH. They are all deleted from your syllabus. So that is why I think with this we have completed chemical equilibrium chapter.